afternoon, ladies and gentlemen. My name is Frederick Poteet. I currently hold my CCNA and will be going over wireless communications and voice over IP with you today. Let's go ahead and start with my personal favorite of the two, wireless communications. Everyone is familiar with wireless routers, such as the ones in your home, and wireless access points like you see in businesses and on multiple academic campuses. So in computer networking and network communications, there are multiple topologies, or maps. So we're going to go ahead and start with the terms, technologies, and topologies of wireless networks. First, we'll start with ad hoc mode, which is a topology designed to solve a specific problem or complete a specific task. Ad hoc mode is comprised of independent devices on their own power, building up a network without any infrastructure. To help you visualize this, I will go ahead and draw it up here on the board. An application of this would be, let's say John, Jackie, and Mike are in a car, and John has a file that he needs to share with Jackie and Mike, but no one has a flash drive. They can establish an ad hoc network and share the file over this small interconnected network. John, Jackie, Mike. As you can see, John has now shared the file with Jackie and Mike. Now before we continue, we're going to need to become familiar with a few terms. First, there's the Basic Service Set, or BSS, which is basically the signal boundaries or parameters generated by a device, which as you can see here are these circles. BSS. Next, there's the Independent Basic Service Set, or IBSS, which is the accumulation of BSSs of all the interconnected devices. So in this situation, the IBSS is going to be the accumulation of our devices, and being so will be our ad hoc network. Then there's the Basic Service Area, or BSA, also called a cell. The BSA is the range for an individual access point within a certain area. So here we'll draw our access point, antennas, so basically the BSA is the BSS except for an access point. Next is the SSID, or Service Set Identifier, which is the name of the network or ID of the network that is broadcasted out to Wi-Fi capable devices searching for local networks. In your homes, it may be something like Jack's Wi-Fi or the Johnson House. So we'll go ahead and write up here, SSID. And for today, our SSID will be test_1. Now we have the Extended Service Set, or ESS, which is multiple APs on different frequencies advertising the same network. So I'm going to go ahead and erase here what we have on the board. And illustrate an ESS. So as you can see here, both access points are broadcasting the test1 SSID and test1 network, and our device here is able to connect to either AP1 or AP2 respectively. Then we have infrastructure mode, which is the most common wireless topology because it addresses multiple span needs for a company and their network. Basically, if a network has an AP, then it will be in an infrastructure topology. Now, as we move from a non-infrastructure network to a structured network, a key technology that we need to know about is the Wireless LAN Controller, or WLC, which is the brains behind every large wireless network. So let's go ahead and illustrate how this works. The way that it works is the configuration for each AP is put on the wireless LAN controller. The wireless LAN controller broadcasts that information out to the APs on the network that become connected to the wireless LAN controller. So let's backtrack a little bit and then build upon what we've just covered, the access point. An AP works using radio frequencies to transmit data and information across the wireless LAN or WLAN. Now, in order to transmit this data, each AP must be on a channel. What's important to keep in mind here is overlapping APs on the same channel, or as it's referred to in the technical world, crosstalk. Basically, what happens is you have two APs on the same channel and a device connects, and when it tries to fetch information or transfer data, it doesn't know which AP to talk to and the packet is dropped. So how do we solve this issue? Simple. There are two frequencies that are used for APs, the 2.4 gigahertz frequency and the 5 gigahertz frequency. And within these frequencies are multiple channels, and amongst these channels are specific channels that never overlap one another. So I'm going to go ahead and draw out the 2.4 gigahertz frequency and show you what I mean. So as you can see here, we have three main channels, which are in the solid colored lines, 1, 6, and 11, which never overlap with one another. Now, when constructing a wireless network, you want there to be overlap, but not of similar channels. So we use what is called the honeycomb method to determine what channel is assigned to what AP. So as you can see, we've got a network of 8 APs, and we've filled it appropriately so that there's no channel overlap or crosstalk. Now with each AP, the cell size can be adjusted based on frequency and adjustment of power levels. Now, if you look here at our honeycomb, we started in the middle and we've worked our way out. So that way, 11 is always next to a 1 or a 6, but is never next to another 11, as with 6 and with 1. Now, when talking about power levels, there are certain groups put forth to regulate how wireless networks are to work and operate. Three of the most important of these groups are the Federal Communications Commission, the FCC, the Institute of Electrical and Electronics Engineers, and the Wi-Fi Alliance. These three organizations regulate frequencies, power levels, ensure interoperability between devices, and so on and so forth. So now that we've covered these basics, we're going to go ahead and jump into the operation of a wireless network and data flow and the pros, cons, and security issues with wireless communications. To start off, it is important to understand that wireless communications operate in half duplex, or in other words, between two devices, only one can talk and one can listen simultaneously. They both cannot be talking and transmitting at the same time. Half duplex is like a conversation between two people, whereas full duplex is more so an argument, not in the sense of contradictions, but in how information is transmitted. For example, half duplex would be me saying, "Hello, how are you?" to another person. That person receiving that information and then responding. Whereas full duplex would be both of us at the same time saying, "Hello, how are you?" receiving the information and responding back, "Good, how are you?" Now, wireless transmission are radio signals sent across a medium, and that medium being the air. Now, let's draw an office space with an access point, and let's see all the possible issues that can arise as data is transmitted. First, we have free path loss, which is the degradation of the signal. Nothing in the way of the signal, just no range. So here we have the signal's traveling, and as it gets further and further away from the access point, it becomes degraded. Next, we have lead. Lead absorbs signals and stops or prevents communications, which is an issue that can occur in many hospitals, specifically around x-ray rooms, which are insulated with lead. So here comes our signal, here comes our signal. It's either going to hit this and be entirely absorbed, or it might sprinkle through a little bit, but then die out. Furthermore, more degradation due to the lead walls. Then there is reflection, where signal is bounced off of metal objects and the signal is lost. So we've got our signal comes up here, hits this filing cabinet, and then kind of shoots off all the way over here, but eventually finds its way back. Next, we have scattering, which is where signals are scattered by objects or humidity. So here comes our signal, right up here into this humid space, and the signal is shot all over. It can reflect off of things, it can be lost, or it may, if you're lucky, just happen to transmit straight to the end device. Finally, there's multipath, which is the scattering and reflection of a signal that results in splitting the signal into parts, which I demonstrated here with the humidity. What multipath does is it takes the packet, which is a combination of different frames, and the frames are numbered in numbered order to be transmitted, and what this does is split them up. So multipath can result in, let's say we have frame 1, frame 2, frame 3, and frame 4. Frame 1 is reflected and makes its way to the end device. Frame 2 happens to make its way directly there. Frame 3 is lost, and frame 4 is reflected again. So the issue here is you have an incomplete transmission, and therefore the transmission will have to reinitiate and begin again. So now that we've established issues with wireless transmissions, let's cover transmission standards. The basic transmission standard of wireless communications is 802.11, and since its release in 1991, the IEEE has released several new standards of wireless communications built off of the original 802.11 standard. So let's go here. Starting with the first standard release being 802.11, the original, we'll go through all of the standards released from bottom to top. After 802.11 came 11b. 802.11b operated in the 2.4 gigahertz range and increased the maximum throughput of traffic from 2 megabits per second to 11 megabits per second. I'm going to go ahead and abbreviate throughput to TP. 802.11a was the later twin to 11b. However, 11a operated in the 5 gigahertz range. It increased throughput to 54 megabits per second and utilized a new transmission method known as orthogonal frequency division multiplexing, or OFDM, which chopped up the bits and spread them out to be sent and reorganized at the receiver. Sadly, 802.11 was released in 1999, approximately 10 years too early because devices weren't capable at that time of communicating efficiently on the 5 gigahertz range. In 2003, 802.11g was released, which matched the maximum throughput of 11a at a cheaper cost. Expanded frequencies from 2 MHz wide to 20 MHz wide, and was now backwards compatible with 11b. BC here, as I'm referring to, means it's backwards compatible for our chart. In 2009, 802.11n was released, which supported 2.4 and 5 gigahertz, expanded channel width to 40 megahertz wide, utilized block acknowledgements, and prevented more interference than ever before. It also introduced multiple in, multiple out multiplexing, or MIMO, which used a certain amount of antennas to transmit data and a certain amount of antennas to receive data. At the time, 3x3 MIMO was the maximum. In 2011, 802.11 AC version 1 was released, which allowed for 4x4 MIMO and grew to 160 megahertz transmissions and over an 80 megahertz channel. Now, as I established, version 1 was released in 2011. Earlier this year, the beta for version 2 was released. However, I do not currently have the updated data for that. Now let's move on to creating and communicating on a wireless LAN. In order for APs to be linked and united as one, there is the wireless LAN controller, as we established before. The wireless LAN controller, to refresh, is the brain and uses a special kind of code in order to communicate solely with all the APs, which traverses the network without interruption. This is called CAPWAP, or Control and Provisioning of Wireless Access Points. Basically, the wireless LAN controller does all the heavy lifting and the APs just do the real-time work. This is considered split MAC, which, by definition, is where the wireless LAN controller now takes over authentication, packet movement, and reconstruction of the frame, while the AP does the real-time work, request to sends, and clear to sends. Now, of course, this goes into much more detail, but we just don't have that kind of time today. So let's jump to security. In wireless communications, there is 802.1x, which is a port-based network access control that takes the authentication and security away from the wireless LAN controller and moves it to what we call a radius server, whose sole purpose is authentication. So I'm going to go ahead and add a radius server here to our network. There are also other securities, such as implementing a firewall that blocks and filters access to specific ports, making access to areas restricted, implementing credential logins to reach certain destinations, so on and so forth. Things seem pretty secure, so where does the security threats lie? According to the FCC, the air is free space, meaning that anything goes across the air, data-wise of course, is available and open to all persons. Therefore, we get issues such as rogue APs, which are set up to steal information and forward it off to another server and be used for any purpose. There are also issues such as service corruption, which is where a device connects to a network and floods the network with a virus or protocol that denies service. These are also known as DOS attacks. So here, we have our end user who's going to connect to test 1. However, we now have the rogue AP who mimics the same network connection as AP2 here and will actually allow for connection out to the internet. However, it does not go through the same connected network as test 1. So as information here is being transmitted, it is also being sent off to the server where the information can be stored and reused by the owner of the rogue access point and the server connection. With that being said, let's go ahead and call it a day on wireless communications. Next, we'll be moving on to voice communications, or technically speaking, voice over IP, which is the transmission of telephone and voice data over the internet. Historically, voice data had been transferred over a landline, where the cable connections were punched down into a connection box, which led to the service provider. Today, connections are made through Cat5e and Cat6 connections to the network, where the data is traversed to the service provider's network and forwarded out as a data packet and not an analog signal. And then forward out. So as you can see here, in the old diagram, the different twisted pairs actually had to be punched down and the connection was sent out to the internet service provider as an analog signal and then transferred. Whereas today, plugged in with Cat5e or Cat6, transmitted to the ISP network and then sent out. Voice over IP, as it is referred to in the technical world, although it holds many differences with wireless communications, actually operates in a similar manner. Just as wireless communications use CAPWAP to communicate with the wireless LAN controller, Voice over IP uses Session Initiation Protocol, or SIP, to communicate with the call manager, or in the Cisco world, the CUCM. In the voice world, the call manager acts as the brains, just as the wireless LAN controller does in the wireless world, for the phones. This is how all the phones are configured, managed, and different changes are added to them. Now, contradictory to wireless networks, the modern voice system traverses the network through the PSTN, or public switch telephone network, rather than the WAN directly. Within the CUCM, multiple clusters or phone groups can be configured and modulated to suit each group of users within a region or area appropriately. For instance, within a hospital, there are multiple practices and multiple levels of employees that have different needs. Phone systems are generally basic in how they are configured and operated. It is the actual phone configurations that vary upon each client. So we're going to go ahead and draw out a voice network, just so you can visualize. So as you can see here, we have 24 standard users and 11 admin users. We have our voicemail server and our call manager. Our call manager, using SIP, controls the configurations of the phones. Now, each phone in the Cisco world has somewhat between 4 to 8 programmable buttons on the main body of the phone. And with newer models, a sidecar consisting of 2 pages of 16 buttons can be added, allowing up to 32 configurable buttons on each sidecar. With each phone, a different phone number can be registered to it, and multiple lines can be registered to a phone. Because in the world of telecommunications, you are not purchasing a phone yourself. You are actually purchasing a phone line that can be put on different model phones according to what your company desires. Now, not all phones are physical. There is also e-phones, which are virtual creations and representations of real physical phones. With e-phones, the physical line is registered and virtual phone is put onto your computer, and the virtual phone communicates to the router, which communicates to the ISP, and the virtual phone is registered. Now, there are also other modes of communicating using voice over IP, which doesn't require a phone line to be purchased, such as Cisco Jabber, Skype, FaceTime, and recently Google's WebRTC, which is a soft client that allows you to configure a phone line for no cost. WebRTC is set up through Basic Application Programming Interface, or API configurations, and the step-by-step instructions are provided by Google. Comparing to the current voice IP numbers, WebRTC in the last 5 years has almost doubled the growth of voice over IP in its initial 10 years. With this, the voice realm of network communications is still growing and has a lot of future progress still ahead of it. That's all for me, ladies and gentlemen. I hope you found this segment interesting, and I would like to thank you for watching. Have a great rest of your day.